Okay. Quote of the day. Remember our the giants upon whom we built the distinct element method? Robert Hooke, the concept of a stiffness, and Isaac Newton, the concept of law of motion. And I got just a little quote about Newton here. And we say Isaac Newton cracked the scientific enterprise wide open. Remember, this was 1687. He discovered that a few mathematical equations could describe the way things move, both here on Earth and up in space. Considering the power and simplicity of his results, one could easily have imagined that Newton's equations reflected eternal truths etched into the bedrock of the cosmos. Basically, everything was done. It had all been figured out. But Newton himself didn't think so. He believed that the universe was far more rich and mysterious than his laws implied. And as this book goes on to describe, the centuries since have abundantly affirmed this, right? We now have a concept of field. We have field theories for electromagnetic fields and relativity and all that kind of stuff. Things we're still constantly trying to get a deeper understanding of things. But remarkably, for the world of mechanics and most of engineering, we're dealing with things at the macro scale, and this F equals ma is like very, very useful and accurate. And so that's the world that we're living in: stiffness and force and acceleration and motion. Okay, today we're going to really delve into calibrating a bonded particle model, and we're going to do most of that work using a fish environment that's been created to help support creating bonded materials, and then also performing laboratory tests, direct tension and triaxial compression. And then the final lecture will be next week. We're going to do a broader look at microstructural rock models, not just bonded particle model. And then I'm going to talk about this latest bonded particle model called the substring network, Breakable-Voronoi model, and maybe give some closing thoughts. Okay, let's go. I'm supposed to hit this one today, lecture 14. So, calibration. Calibration has to do, how do we make the model behave like a rock? What does that mean? How do we know how a rock behaves? Well, that's because we have different scientific theories that talk about behavior. And so we talk about behavior in our world. We're thinking about things in terms of deformability. When you squeeze it, how does it deform? And where are the forces and stresses when you squeeze it? And then we have concepts of strength. Strength is a slippery beast. It all depends kind of on what sort of strength, right? When you say strength, do you mean complete failure? Do you mean the beginning of damage? Do you mean operational failure? Maybe it's failed a little, but it's still safe enough. And in rock mechanics, there's two kind of the most fundamental things, is that we talk about taking a material and compressing it, and then we talk about taking a material and pulling it. And in the world of rock is quite strong when you compress it and quite weak when you pull it apart. And this was known already by people in the Middle Ages when they built cathedrals, for example, right? They would build cathedrals out of stone, and pretty much they built them in such a way that almost all the load was compressive on these things. So let's talk some more then about these things. So like, what are these properties that we're going to typically measure in rock mechanics, and then how do we get them, right? So let's turn to the slides. So I'm gonna go here and say share my screen. Okay, we should have screen in 3, 2, 1. And can you see this other screen?
Yep, we can see that.
Fantastic. Okay. Now Can you see? Here we go. The Autumn Festival. This was the end of the previous lecture. The Mid-Autumn Festival. Okay. Now, and you can see me as I say hello, right?
Yep.
All right, excellent. Okay. Properties. So, let's start and just review quickly. We talk about the formability. And if we assume, remember, any kind of property really is just something related to a theoretical description of a material. And a theoretical description has associated with it certain parameters. And so if we use theory of elasticity, and we say that the material is linear elastic isotropic, which pretty much all materials are under small deformation. That's actually what Hooke figured out in 1685. That's what he, from all sorts of experiments. And then theory of elasticity comes along and we say there are two parameters. And they can be expressed as Young's modulus and Poisson's ratio. And so if a material is linear elastic isotropic, if you can know those two values, that means you can solve for the deformation of any boundary value problem. So you can have any shape of a body, and you can have loads on it like this, and you can have fixed side, and now you can solve this problem of how it deforms if you know E and nu. And this just has to do with how it deforms. It's typically small strain, and there's no damage happening. So strength is not a concept yet when we talk about deformability. And there's also, though, an issue in rock mechanics. You guys tell me this. If you take a cylinder of rock, and the simplest possible test I could think of in the world of rock mechanics would be to put it between two steel plates. And typically that's fixed. You just set it on a steel plate and you apply a force P and you measure delta, right? And when you do this, you come up with axial stress. You measure axial strain. And if you measure this, what you will get is a straight line. This is contraction positive. This is compression positive, right? And what's the slope of that line? Somebody, throw it out.
E. It's yeah, modulus.
Young's modulus, right? Now, if we take in the world of rock mechanics the same, a rock, though, a typical rock, and this would be called a UCS test, unconfined compressive strength, okay? And it's only under these UCS test conditions, we'll talk about that a little bit later, that you actually, if you plot stress and strain, that you get the slope is E. If you do an odometer test where the sides are constrained and you plot stress and strain, that is not E. And if you do a rock mechanics test, and I'll say it's a tensile test, which is very much less. People don't do these very often because they're hard to do. And so if you could somehow grab it on the top and somehow pull it, you would again measure, and this time stress and strain. Now I'm using a different sign convention. The strain is, this is extension, and this is extension. And again, you'll measure a slope, and that slope by definition is E. But how it, in general, for most rock, how is this, let's call this ET, and let's call this EC. How are they related?
The ET will be smaller than EC.
That is correct. That's what we typically will measure. And then what's the mechanistic reason for that?
Because the when we compress the rock, the crack will be closed, but when we make a tension test, the crack will be there and just start to break.
Yes, not break, but stress. So what you're saying is there, in most rocks, there's initial flaws, I guess. And these can be pores, slits, gaps. People typically call these types of things, they'll often call them cracks. Cracks basically means a very thin two surfaces pushed together that have been slit open, right? And so if you have a material, I'm going to try to draw it like this. This is a simpler way to draw it. And if you actually have, like, let's just exaggerate this, but you have this thing like that, and you have three, say you took a machine and you machined in three little gaps like that, and they're oriented in that direction. And so if you pull this, those surfaces are not participating in providing any stiffness if you pull it. And so you'll get a certain resistance, which the slope of that thing is going to be your modulus. But if you push it, that surface is going to close, and now there's going to be traction on it. And so that is now going to be stiffer. You can think of a system, you can always think of a body as made up of a whole bunch of springs. And if a surface comes together, now suddenly there's more resistance. So there's an additional spring in there. And so that, in that case, then it will be stiffer. Okay. And for this thing called, to just give you a rough idea, for this thing called lactobonic granite, the compressive modulus is about 69 GPa, and the tensile modulus is about, I can't remember, 47 GPa. They call, and so notice one thing right away. If you have a material that has gaps and things, and it starts to change when you squeeze it, that means it's not the same material. It really isn't obeying linear elastic isotropic material. If it's a theoretical linear elastic isotropic material, nothing changes when you squeeze it or pull it because it's isotropic. The stiffness, all of the deformability is the same, both on compression or tension. So this is, even this simple case is demonstrating that rock is more complicated than is described by a linear elastic isotropic thing. However, in most cases, especially for design of rock mechanic structures, we usually just ignore this, and we almost always just take the modulus that you get during a UCS test. Okay, are you with me?
Yep.
Yep, okay. And notice another thing, if you recall, when we looked at the UCS test and we did stress versus strain and we looked at the real curve for lactobonic granite, it does this stiffening, then it's linear, and then it starts doing this. So that means the slope is changing, right? The initial slope is this, and the slope up here is stiffer, and that's because of this crack closure business going on. And so what is typically done is there's a portion of this curve that's almost linear, and then that's the slope that people measure, and they call that the Young's modulus. Okay? And there's different times, usually, like sometimes people will take like 50% of the peak, and then they take the tangent modulus here, and they call that EC. For many, many rocks, though, this is a pretty minor effect if they're very well connected, if they're like, many rocks are relatively well connected. And so, but this is often not really an issue as long as you take this measurement after this initial closure business. And so then this is what gets assumed, okay? And so this is what you will find in the literature. This is what people will measure. So I have this is super cool. I have a really good example. So I'm working for this company, an oil company in Thailand, PTTEP. I don't know what that stands for. It's a big oil company in Thailand, and they have a rock mechanics group, and there's a new sandstone formation that they're going to develop, which means they're going to try to get the oil out of it. And so they need to characterize that sandstone. So they need to do these sorts of tests. And so this is the first thing that they've done. They've given me some data here, right? And of course, the data they've given me is this E. And their stress strain curves, for an odd reason, they don't start at 0. They start offset, and they're pretty much a straight line, and then all kinds of stuff happens later on. And so I was talking to them like, what the heck? What's going on? I'm expecting this sandstone is going to have initial cracks and voids. And this is also very common. They say, well, look, we often don't do these tests. We contract with a company to do the tests. And what they believe is the company just doesn't want to bother with this nonlinear business. So they just don't worry about that. And the data that they give you is just this linear portion. And so they couldn't for sure answer this, but they can give me this value because I can take that slope, right? Okay. Now, what about Poisson ratio? How do we get Poisson? Here's the UCS test again. How do we get Poisson ratio? It's going to be a slope of what? Well, it has to do with, what's it measuring? When I squeeze something, what does it typically do? Does it change shape?
Oh yeah, it will change the lens in two different way. How can I say that? I forgot the name of it.
Yes. If you squeeze it, it will deform. Let's put a coordinate system in here. X, Y, it will deform in the Y, and it will also bulge out here, typically bulging out in the X. Just take your rubber eraser if you have one and squeeze it and it'll bulge out. That's a very typical thing. And so if we define our coordinate system like this, X and Y, and if we take this and turn it into strain by dividing delta Y by the original Y, right, and delta X by the original X, then Poisson ratio is defined to be, let's do this. If we plot, if we plot strain in the Y versus strain in the X, so this is going to be extension positive, and but this will be compression positive. And so in that case, this will also be a straight line because it's behaving linear elastically. And then this will be the Poisson ratio. So the Poisson ratio is minus the strain in the X over the strain in the Y. If you apply this much, 1 unit, and it bulges out 0.2 units, then the Poisson ratio is 0.2 because they're opposite directions. You squeeze it, it's a negative value, and it extends, that's a positive value. You get a negative ratio, but then you switch the sign. That's why there's a minus sign here, because you want this to come out positive. It's more convenient. Okay. So are you with me? Okay. And to
Yep.
be perfectly clear, I should label this, that's what you measure in a UCS test. And if you did a tensile test, you should also measure something, and it actually also would probably not be exactly the same, but I'm not aware. I'm sure people have measured this, but it's definitely going to affect things. Having if you have this initial set of damage. In fact, if you squeeze this here, if you start having more and more cracks, it basically makes the thing bulge out more. It's going to increase the Poisson ratio. But let's not worry about that. So, to summarize the formability in the simplest way, so in the simplest way, a linear elastic isotropic, good. We need two parameters. We do two tests, UCS, direct tensile test. We get these two things. We typically don't care about the ET. We typically just take this one. So we usually just do a UCS test, and we get both of these parameters, E and nu. And by the way, if you had a shale, and a shale rock is like highly, like super bedded, like at a very small scale, okay? They call this shale. And this rock now is even more complicated because it's not linear elastic isotropic. If you squeeze it this way, it's going to be different than if you squeeze it this way, the way it responds, because it has to do with this complicated orientation. So you're going to get the formability is going to be more complicated. And so instead of linear elastic isotropic, you say it's transversely isotropic. And basically, if you use theory of elasticity and you assume certain symmetry that corresponds with this, and then you come up with, I'm not sure, it's either 5 or 6. You get like 5 independent constants. Wood is an example of this. If you have a beam of wood, I do a lot of woodworking, and you take a big 2x4 like this, and you load it. It depends on the orientation of the grain. That wood is made up of fibers. And so if you load it in different ways, it has different stiffnesses and also different strengths. And so if this was your material, you would actually need to do tests at different orientations to the bedding plane. And if you do a proper set of tests at different orientations, you can back calculate based on the different slopes these 5 independent constants. Okay, so we're not going to worry about any of that stuff. Many rocks do not have this directional bias. So in the simple case, again, we're just going to need 2 things, E and nu. Oh, and here's another thing. Remember I said this test, direct tensile test, this is a direct tensile test, is often not done in rock mechanics. It's a pain. You'd have to take a plate of steel and use an epoxy and glue it to the top. And you'd have to glue the bottom to some big steel plate, and then you could do a test like this. But someone figured out at some point that if you take a cylinder and if you turn it on its side so that now it's like this, and I'll rotate it again so I'm just looking at it like that. And now if you take 2 steel plates and you push it, now this is a complicated boundary value problem. This is not a uniform stress field. If I have this case, the cylinder, and I push it, I get uniform force chains. Everything's the same everywhere. In this case, you don't. It's complicated. You're just loading a point here. So you end up getting the forces are flowing kind of like this. And so the result is you can solve the theory of elasticity problem, assuming that this has an E and a nu. Remember, I said if it's linear elastic isotropic, once you know E and nu, you know everything about how it's going to deform. And it turns out that along this line, you get a pretty high tension force. Call it sigma T. And so if you load this thing in this configuration with P, and if you plot P versus delta, no stress and strain now, just P versus delta, where that's delta, what you will get is you will get a thing like this, and then it will break, and you can relate this value, P prime, to what's called the tensile strength, sigma T. I've jumped ahead of myself here. But this is a way of measuring tensile strength now. Now we're going to talk about strength. And the simplest possible strength, one could argue, is a direct tension strength. Take a bar, take a cylinder, you pull it apart, and usually, if this is P and this is delta, it'll go up, and then it'll usually abruptly break. And if you just pull this P over area is stress, right? And this over initial length is strain. That's what we did before. And so then from this test, you would not only get the tensile E, but you would also get this, which is the tensile strength, sigma T. And so this would be a very simple measure of a strength. If you just pull something in tension, it's going to rupture, and it will typically, there'll be a few little cracks, but very few, and then it will just typically tear itself into two pieces. And the Brazilian test comes in here because in rock mechanics, as I said, this is hard to do. So instead, you do this, and they call this a Brazilian test. I don't know why. A Brazilian test. And then based on the theory of elasticity, this stress here is a function of that P and the diameter of the specimen. And so there's some relationship, and I can't remember what it is. I think it's like pi squared D or something like that. And that's what you do. You measure the P and you compute then, assuming these conditions here, what you call tensile strength. And typically then they call this sigma B for the Brazilian strength. Now this is not the same problem, right? This is failing because a crack will kind of start in the middle and grow to the sides in a brittle fashion. That's not the same as over here where you're just pulling it apart. And so then it turns out then that this sigma B, think of it this way, the actual direct tensile strength is usually some multiple of sigma B, and this thing might typically be about 0.8. And depending upon the rock, it's going to be something different. Which means the Brazilian strength you measure is like 10 units, but the actual, if you pulled it in direct tension, it would only be 8 units. It would fail earlier. Okay. So people with me? So for strength, the simplest thing is tension, direct tension, and they call this tensile strength, right? So tensile strength, and I'm going to denote that by sigma T all the time. And again, you look up any rock and they have this. Well, that's not even true. So the PTTEP guys, right? They have these samples that they sent off to a lab of a certain sandstone, Bandera sandstone, and these guys did these triaxial tests. Forget that. They basically did a UCS test first, and they can come up with E and nu, and then they can come up with a UCS. We'll talk about that in a minute, the compressive strength. And then so I say to them, well, yeah, what's the tensile strength? And they say, I don't know. I say, oh my God, you've got this you don't have the tensile strength. And they're like, yeah, no, that's kind of a pain to do. We very often don't do those tests. And so that, but there's some paper where people did do that for this particular rock. And so, they do have that, their UCS is 10 times bigger than their tensile strength. You're going to find that when we calibrate a bonded particle model, we will try to always start by first matching the tensile strength and then adjusting things to also match the compressive strength. In general, in most rock mechanics situations, there's not very much data. It's quite expensive to do tests. And oftentimes it's even hard to get the material out within being intact. Oftentimes when you drill out the material, it damages it in the process of taking the core. And so there's all kinds of complications. It's not like if you have a steel bar that you buy somewhere because you're going to build a steel structure that's been built in a controlled condition, and you can very easily do tests and measure all these different properties. It's difficult to do that for rock. But if you're going to do modeling, you have to have properties. And so if you don't have this and you want to do modeling of it, then you have to assume things. Okay. So there's direct tension strength. Remember I said that the two simplest things, tension and compression, right? So we do a tensile test, we get sigma T and ET. And now if we do a compression test, we're going to get something, and we're going to get EC, typically a nu C. And so again, in the UCS test, axial stress, axial strain. This is the axial direction, A. And again, it looks like this, and then it's linear, and then it usually reaches in a UCS case, unconfined compression test, it reaches a value that's pretty abrupt, and then you typically get a quite brittle failure. Brittle means that this curve goes almost straight down. And so this value here is what they call some people in the mining world call it UCS. I'm going to call it sigma UCS. So this then is what we call the compressive strength. So for the UCS test, we get compressive strength. With me? With me?
Yep.
Okay, and remember we talked about two types of rock. We talked about, in general, you can talk about compact rock, very, very little initial gaps and cracks and stuff in it. A granite is an example, and you can talk about compact, what did I call it? Did I call it porous rock, I think? And for that, an example is sandstone. Let me make sure, what are we calling this thing? Just a minute. Yeah, compact and porous. Okay. So then a sandstone, and what are some of these typical properties? So or a granite, again, there's quite a bit of variation. There's all sorts of different granites with different microstructures, but in general, they're granites, so they're interconnected crystals. And there's all kinds of different microstructures of sandstone. But if we just take an example, and if we say lactobane granite, sorry, LDB, and let's call this, I have some data for this, we call it Castlegate sandstone. This is a typical one that has oil in it. So E sub C for that granite is going to be 69 GPa. For this sandstone, what do you think? Big or smaller?
Well, maybe it's smaller
Why?
because the granite will be bonded better.
Okay. The answer is right. Sandstone is typically less stiff, and it's basically it's like less connected. There's more porosity and stuff in there. There's less places for springs, if you will. And so for Castlegate sandstone, this is about 3 GPa. It's quite a bit less stiff. And then this new, what the heck is it? So the new for people often talk about for granite 0.24. So you squeeze it 1 unit and it bulges out 0.24 units. And for the sandstone, it's often bulges out more. So this is 0.33 for this particular one. Okay. Now what about UCS? Sigma UCS. Again, that's what typically is measured, these 3 guys. So what do you think it'd be reasonable values? You have any idea? Come on, Shihang, are you there? You must know this. Granite, UCS. Shihang must be eating a mooncake right now. Well, for lactobonic granite, it's about 220 MPa, megapascals. And what do you think it would be for a sandstone, big or smaller?
Smaller, I guess.
You're right again. And so in this case, it's like 20, sorry, MPa.
So it's much more smaller.
Much smaller, yes. And again, it's if you look at the microstructures of these things, they're very, very different. The granite is super well connected crystals, and the sandstone, the more you zoom in, the more voids you see. Typical sandstone might have a porosity. This guy has a porosity, we typically say N, of like around 0.18. This guy has a porosity of like 0.001. And porosity is volume of voids over total volume. So if I take a representative volume and I count the amount of open space, that's porosity. Look at, there's almost no porosity here. And this guy, you know, and these can range, the rock the PTTEP guys are doing is 40% porosity. So it's a lot more open structure. And so therefore that open structure is not able to carry as much load before it breaks. Okay. Now what about tensile strength? What do you think for this granite?
Maybe
Easy
it's
question. Is it
one.
bigger or smaller than 220? Go ahead. What do you think?
Of
Take a
course,
guess.
smaller.
Okay.
Yeah, and I guess it will be like 160 MPa.
Okay. Any other guesses out there? Just think about if you held a piece of granite like your marble countertop. And the problem is you don't have any good sense of this because you can't squeeze marble with your hand or granite with your hand because it's just so stiff. And you can't nearly do it. But if you think about that, think of that marble, that granite countertop. You'd have to put an insane amount of force on that to squeeze that to rupture. But like, think of, you could take that, your countertop, and if you went, and this is your countertop, and if you just put it like this, and if you hit it with a hammer, it's going to break pretty easy. And it's going to break because when you load this like this, it bends, and you get tension right there. So this is like a tensile strength test. And in this case, when that thing starts to form, it just ruptures all the way through. So it's going to be much less,
so
actually.
Will it be 10 times less than?
Okay, that's a good.
It's
that's
like 20 MPa.
So you'd say 20. That's reasonable. In this particular rock, it's 7. And for the sandstone, relative to the 20, it's all the way down to 1. Okay, so it's 20 times weaker in tension. This sucker here, if I take the ratio now, this guy, What the heck is this thing? I'm going to do my calculator. 220 divided by 7. Holy smokes, it's about 32. So it's 32 times weaker in tension. And this guy is 20. Okay. Now, remember I said in the world of rock mechanics, pretty much always measure that. Usually we also, if we're doing anything serious in something that you're going to build, you do those Brazilian tests. And they're quite easy to do because you just need 2 steel platens, which you already have to do the UCS test. And you just take some specimens and turn them on their side. And you get Brazilian strength. So you also typically do this. And what you can use this ratio in general is a way to characterize rock. And for most rocks, this thing ranges from about 2 to about 32. And what you typically would say is when you get here, you get, say, above 12, they talk about hard rock, hard brittle. And if you're on the other side, they talk about soft and more compliant. And you can see how this even this sandstone is still pretty brittle and hard. But this is an important parameter to characterize rock. And so we're going to find out when we want to build a bonded particle model, at the very minimum, we would like to match these things. And what we're going to find out, what we found out the hard way after many years, is that if you build a parallel bonded material, this ratio is basically always going to be less than or equal to about 5. You simply cannot get, if you get a tensile strength, you calibrate it to get a tensile strength, and then you just do UCS tests, no matter what you do, it fails when the stress is about 5 times bigger than the tensile strength. And it turns out this is because you have to have more interlock than you get with a parallel bond. And thus we have things like the flat jointed material and things like that. Another correlation people know is that if they look at the modulus of this, of rock, the higher the modulus, typically the higher the strength. Stuff that's like really, really stiff is often in compression stronger. Okay. Now there's one more thing about rock. Let's see who knows this. Check this out. Okay, rock. Tension, weak. Compression, strong. Now, what if I take rock though? Let's do it this way. This is an excavation, deep underground. And there's high load coming in both ways, typically underground. Underground, the load is pretty much always compressive. So this might be, I don't know, this might be really, really high, like 100 MPa. This might be 20 MPa. Like in a gold mine, it's even higher than 100 MPa. And now think about like here, this region, and think about this part of the area. This guy on the surface is getting squeezed. It's kind of like a UCS test because there's a free surface. But this guy up here is getting loaded with 100 MPa and getting loaded here with 20 MPa, like far away from the excavation. Okay. So think of if I had a rock sample that was sitting like this with 100, I'd get a certain UCS. It's free. I'd get a certain strength. But now if I take that same sample and I squeeze it, let's say with 20 MPa, what do you think I'm going to measure in terms of the strength?
Well, the strength will be larger than just doing a UCS test.
Why?
Well, because actually we have learned this before. It's maybe called a triaxial test, and so the break, it's depend on the larger the like 20 MPa thing is, larger
Mm-hmm.
that force is, and larger the strain is.
It's all correct, but what's the mechanism? Why is that the case? You're telling me that if you do certain tests and apply confinement, it gets stronger. Why? So think of
Maybe it's called because larger the forces, and the the small cracks will be like close and have more contacts, have more springs, so the strength will be larger.
well, what you said means the modulus will be bigger, the deformability because it closes up cracks. But the strength, think about this. People already knew this well before mechanics. Imagine that you had to fix it. You had a chair that had a leg and it was like this, and you're sitting on this thing, right? And this thing maybe is really slender, and so it breaks because your uncle's big fat guy, and when your uncle comes, he breaks the chair, right? So yeah, that would be more like this. Here's the chair, and there's the thing like this, right? And this thing is, there you go, not very big. So you, okay, uncle, heavier, break. Now, what could you do to make this chair stronger?
Well, connect the leg of the chair.
Yeah, okay, that's a good thing. So a woodworker might do. You might put another piece of wood here and make it stronger. But let's say that this thing isn't quite the perfect example. Let's say if it was more like this, and that chair leg was a thin thing like this, and it was perfectly balanced so that it was going to break. And what if you took this and you put bands of steel around it? Okay. I would argue that that would reinforce this and it would be stronger. Think about your rock specimen. What happens when we do a UCS test? What happens to the sides of this?
They bulge.
They bulge. So think of it this way. So in a UCS test, when I apply load, this thing wants to bulge out. It naturally does. Okay. And that's part of the reason then why you get these cracks that form in this direction. And eventually, when you do a stress strain curve, they go up and you start getting all this cracking here. And then eventually it breaks, and it tends to break into big pieces. They call this axial splitting. Okay. But if you took that same rock specimen and you put bands of steel around it, now it's inhibiting the bulging. And so the result is it's not able to fail the way it wants to fail. It's going to be stronger. It turns out that most that rock, not steel, but rock, locally, internally at the grain scale, is pretty much almost all microtensile failure. And so if you put bands around it and you apply, we call this confinement. And so if you increase the confinement, you end up increasing the strength. You make it harder for these cracks to form. And if you, so instead of putting steel bands, you just put, think of somehow you're putting a pressure on there. Confining pressure. I don't know, sigma prime. And this is now P. The way they do this in a laboratory is they take a cylinder of rock and they have a synthetic, it's like a balloon, some kind of crazy membrane, and they put the rock inside the membrane, and then they make a special cap, that's the platen, above and below, and then they somehow hook in this membrane to the sides, so it totally surrounds the rock. The membrane also goes around here. And now, as far as the rock is concerned, its boundary condition is what I drew. Pressure, they actually apply delta, right? And they measure P, so they're applying P, and they maintain this pressure. It's usually in it's a hydraulic system, some kind of hydraulic fluid, and they maintain this constant. And we call this a triaxial test, because now the material, if you look at it, is not only being loaded this way. In this system, that's sigma 1, and there's nothing here, it's 0. But now it's loaded like this, sigma 1. And then you have all around sigma prime. If you look down the cylinder, it's got this, sigma prime, right? And looking straight down is sigma 1. It's a different loading condition. It's confined. And when rock is confined, it's stronger. And so if we go back to this stress strain curve, if you now apply confinement, what will happen is it will get stiffer for the reasons that Yoon King said, because it's more compressed, those initial cracks or whatever's in there, it's more compressed, it'll tend to get stiffer, and it will go up higher till it fails. And then if the brittle case, it'll go all the way down because it just splits apart. There's right away, there's no more load carrying capacity. This guy still has load carrying capacity because it's being confined. So it'll tend to do this. And then if you put more, it'll do this. So this is increasing sigma prime. Are you guys with me?
Yep.
This is what Yoon King recalled from what she was telling us about, right? So, and the reason we care is, again, for this reason. This is where's my excavation? This is my excavation. So far away from the excavation, the rock is confined. It's stronger. When you make an excavation, you're changing the confinement and the rock gets weaker. Think about if there was no excavation. The rock's just been sitting there for 1,000,000 years. It's totally able to sustain this amount of stress. But now we make an excavation, everything changes, the boundary conditions change, and there's no stress on this face. And it's kind of like a UCS test. And so it's weaker. That's why rock gets damaged when you make excavations. You're changing the loading. And so the take-home point of this, and the last thing, if you take these values of sigma prime, they're increasing. And if you, we're not going to go into this too much, but did you guys talk about more Coulomb? Not more Coulomb. You talk about, oh my God, what's this called? This is the transformation, Moore's circle. Have you heard of Moore's circle?
Oh yes,
Probably,
I know that.
some of you have. If you load a material this way, like this, that's sigma 2. If you resolve the tractions on this thing, there's a different traction along here and along here and along here. And you can end up doing this business, sigma 2, sigma 1, and it turns out that the shear stress along this interface is related to the orientation of the interface. And so if you have a certain confinement, you'll get this. If this is 0, but now you'll get this. Sorry, you'll get this. And then if you apply a higher confinement, you'll get this. And so basically this is relating to shear strength. This would be the maximum shear stress in the thing. And then people do a fit to this, and they take this and they call this the friction angle. So that's also a typical thing. It's called a friction angle. This is called a Moore-Coulomb idealization of the rock strength. Because remember, the rock strength, the UCS, is not enough. You also need to know how much stronger it gets as you confine it. Okay, and that's measured by doing these tests, triaxial tests at different confinements, and then interpreting these values in terms of these Mohr circle failure envelopes, and you get something like this. The idea being, if your shear stress, if you're outside of this envelope, it's failed. And if you're inside, it's okay. And notice, if it's confined, it's got a higher strength than if it's unconfined. Okay. Is everybody with me?
Yep.
Yes.
So this is as far as we're going to go in terms of strength discussion. So direct tension test. Help me again. You measure ET and you measure tensile strength. You take this, you put it in a triaxial cell, and usually if you have a triaxial cell, they're quite expensive. You could put this in confining fluid and just put super small confinement on it, and you could say that's like a UCS test. Or you just do a UCS test, which is easier. It just that you can see the specimen just sits there. So then you measure EC and nu C, and you measure sigma UCS, right? And then you do some confined tests in the triaxial cell. You apply, sigma confining value. And now based on all of that, remember, you get stress strain, goes like this. You take these peak values, you go to that Mohr Coulomb thing here, you get a slope and you call that a friction angle. And so from this, you get friction angle. And this is probably the simplest possible way of thinking about strength of rock. So we talk about strength of rock, tensile strength, and then this, UCS and friction angle. Because if you know the friction angle, you know what these values are. Okay? So you measure some of these values and you do this fit, and you come up with this friction angle. So the key thing is you're figuring out these things. You're figuring out how it's getting stronger. And some rocks, if it's a higher friction angle, that means you apply a little bit of confinement, it gets much stronger. I'm trying to remember, the UCS granite is an extreme case, the LDB granite, and I'm trying to get back, sorry. Here, remember, this is the granite, that particular granite. It has a UCS of 220. If you apply, I got to look this up, but I think if you apply like 5 MPa confinement, this thing goes up to like 300. And with just small amounts of confinement, it's much, much stronger. Other rocks, like it's going to be a lot less for a sandstone. It's still going to get stronger, but it's not going to be as big of an effect. Okay. So, are you with me? One could argue that these are like the basic, if you're going to build a bonded particle model, you really probably should match at least these things. Okay. And so this is going to be what we're typically going to do, or at least as a starting point, when we try to match, when we try to construct a synthetic rock. That's a bonded particle model. Okay. And just one last quick thing for completeness here. There's a whole entire branch of mechanics called fracture mechanics. And fracture mechanics looks at the following problem. If I had like a thin plate, so this is thin, this could be any material. Linear elastic material that has a certain B. Okay, let's not worry about that. If I apply a far field load to it and stretch it, think of that. You could hold a piece of paper in front of you and pull it. And you got to pull it pretty hard, and eventually it'll rip in two. But if you take that same piece of paper, you take out your pocket knife and you put a slit in it, and now you pull it, it's gonna go boom. At some point, nothing's gonna happen, and then boom, it's gonna like rupture across there. And this value is significantly less than this value. And if you do the same test and you put a longer crack in it, it's going to be even weaker. And it turns out that fracture mechanics is studying this whole process. How does a material get weakened in the presence of a crack? A crack is a giant effect on strength because it's a super weak point. Think of it like this. In this problem, that's a crack. Remember that force chain business? I'm pulling on it. Far away, the force chains are just going straight. This force chain is trying to go across, but it can't. So it has to work its way around. And this guy's trying to get across. He has to work his way around. And it turns out for a crack, the stress at the tip here, the theoretical stress, so if you plot, this is X, this is Y, you plot sigma Y along this line, far away, it's equal to the applied far field sigma. As you get closer, it goes like this, and it actually is an asymptote to infinity. The theoretical stress of a linear elastic body at a crack, what's a crack? A crack means a surface where this angle is equal to 0. It's the limiting case where this thing is perfectly two guys. That tip is infinitely sharp. And the stress, like if you had the stress here actually is infinite. And we know in real materials it can't be infinite because something has to give. And so fracture mechanics basically is a way of characterizing, they call this a singularity, and characterizing that, and you end up coming up with a thing called fracture toughness, typically denoted by this. And you can measure this by doing these sorts of tests. And then you can say that another important parameter is fracture toughness. But you have to do these sorts of tests. Okay. And so if there's big cracks and they're somehow causing the failure, that should be also thought of, and that's this thing called fracture toughness. This is not used that much in rock mechanics, but there are many problems where this is important. And just because I'm a storyteller guy, fracture mechanics, 1940 to 1945, what was happening in the world? What was happening in the world? Big time.
I guess World War II.
Correct. World War II. What was it? There's all, you guys are all Chinese. A lot of you are Chinese. Was it 1949? Revolution?
Yep. We got the nation in 1949.
Correct. Correct. And I think a person that was called Mao Zedong was a big leader at the time. Was that right?
Yep.
Got it. Okay. Well, let's go back to this period. Big, huge World War. So, World War started in Europe. It took many years until the United States got involved. I'm not sure, maybe 1942. So the US, so here's Europe, here's the United States, US, USA, Europe, here's the war. So we had to send all kinds of material across the ocean very fast to help support, we used to call it the Allies, like Britain, France. And so we had to actually construct special ships to convey so much material, and we didn't have those ships. So we built a whole fleet of just transport vessels very quickly. And so we didn't use the traditional building techniques because it takes too long to build. And I don't know if it was hundreds of these or dozens. It was quite a few of these ships. So what they did is they just took steel plates, and I'm not sure what this size might be. Maybe this is 10 feet. And they took these relatively thin steel plates, which you can make these really fast, and you just put them together, right? And you put another one, and you just do this. And here, You do a welding. It's a way of joining metal. And so we can fabricate these ships very quickly. So, you know, they're basically like, think of it like a barge, right? Here's the ship. It's just like a big giant cylinder, not a cylinder, big giant thing like this, and it floats, right? Here we go, floats on the water. So they built these things. They called them Liberty ships. Liberty ships. Great. Everybody was happy. These things worked. They could build them very fast. They started putting tons of materials over to Europe, and as you know, eventually the Allied forces won the war and defeated Nazi Germany and Japan. Now, there was an issue, though. You would get to Europe, and these ships, you know, when they're getting loaded, they're just sitting there in these harbors, right? And they're getting loaded. And suddenly, one of these ships just like sinks. It's just sitting there, and it actually cracks into two pieces, and it sinks. What the hell? That's not a good thing. Well, it's just one. Who knows? No big deal. Well, pretty soon there were many of these things. These ships started just sinking. They'd just be pretty much just sitting there. They're not getting loaded in any special way, and they just fracture. Boom. And so because of this, and no one understood why. And so because of this, it led to, there was lots of research done, and it led to the development of fracture mechanics. And these ships, it turns out, were sinking because when you weld something, especially if you don't do it very, very carefully, and this was done very quickly, if you look at detail at this interface of the welding, there's all kinds of there's little cracks you introduce. Okay? So those cracks are there right from the beginning. And remember what we said about cracks. If they get stretched, boom, they can go. And they can weaken things. You can actually, I'm not really drawing them the right way. The critical way is this way. When you weld, there's also cracks going this way. So now when this thing gets stretched, these guys can rupture, right? So it's kind of like this kind of situation. All these weird cracks, and it's getting pulled. Boom, the strength is much, much lower. They didn't design for this. It didn't exist. Nobody thought about fracture toughness. They just designed this based on tensile tests and bending tests, the first type of analysis we talked about. And so this was, fracture mechanics arose because of that. And so it was able to explain this issue of why this happened. And so nowadays, this is especially in any kind of metal structures, aircraft, for example, as well. Fracture mechanics is fundamentally thought of. Anybody who does mechanical engineering design knows about fracture mechanics. And so they definitely measure things like K1C. Okay. It may not be quite as applicable if this is an excavation deep underground. There's not necessarily often an issue of fracture mechanics, but if you, maybe there's a joint set like this, right? And now you could start thinking of those joints are kind of like those welded joints, and you might start thinking of this in terms of fracture mechanics and fracture toughness. Okay. So that's all I'm going to say about the properties. Any thoughts? Does it make sense?
Yep. And I actually thought the fracture mechanics are begin with the like airplanes or something, but I never thought about that. It was begin because the World War II.
Yeah.
That's
Thank you
also
for
part of
sharing
the
the history.
Yeah, that's also part of the story. My advisor, as a PhD student, Tony Ingraffi at Cornell, he was a big fracture mechanics guy. He used to tell this story in his fracture mechanics class. And also in aircraft, there were also many, many failures early on in aviation history that were not explained. You would have a plane. Oh God, see if I can draw. There's my plane. You get the idea. There's a plane flying, and suddenly the wing would tear off. And again, there was a long period of people trying to understand that. And again, it turned out to be the fact that if this is like for example, this might have a cutout for a window, So this is the fuselage of the airplane. And now you got a window, and when you fly a plane, you often, well, let's not even worry about that. You got the, yeah, well, that'll be one thing. You pressurize the plane. You know, that's why your ears pop and stuff, right? Pressure's lower, so they typically put pressure inside, which means the skin of this material is getting stretched in all directions because it's a tube that's getting pressurized. And so, again, depending on how these things were fabricated, you would also often get small cracks in there. And again, it massively weakens the structure. And then if you're in a tensile field, if it's tensile loading and you're in a tensile field, this crack just boom, it goes brittly. Okay, so this was a big thing. There's all kinds of interesting history. It took quite a bit of time. And this, while we're here, just to go for this quick, this was actually something, this is typically not a single loading. It's called fatigue loading. And so this means, think of that of a paper clip. That's the perfect example. You know what a paper clip is, right? You may have one on your desk. Just bend it between your fingers. Just flex it. Do that about 12 times. It will break. And that's an example of fatigue loading. Every time you flex it, you get tension down here, but it's not enough to break the material, but every time you flex it, you have a tiny crack there. And every time you flex it, it grows by a small distance. So if you have enough cycles, eventually the crack reaches a point where it's so big that now it's weakened the structure to the point that the next time you load it, it breaks. And so we call this fatigue. And that's typically what would happen in these aircraft. That's why they would be flying for a while, and it wasn't until, you know, a year later they went on a flight and suddenly the thing broke. This is still a big issue in aircraft. In fact, every aircraft that you fly in has a complete inspection, and I don't know what it is. I have a friend who flies the Boeing, the Delta airplanes, those big 737s and things, and he took us for a tour a while ago of the Delta maintenance facility, because it's in, one of them is in Minneapolis. And oh my God, it's either 3 years or 5 years, Delta. They completely tear everything out of the plane. They take all the seats out. They get it all the way down to the fundamental fuselage and frame. And they literally have guys that climb around and inspect every single square inch of that thing to see if there's little fatigue cracks. And then if there are, they replace those components. That's how big of a deal this fatigue business is. And of course, it also occurs in rock. But there's not as many situations where this necessarily is applying. And the last thing, remember we talked about UCS test of rock. Well, fracture mechanics applies even at quite small scales. And so people do analyses of when I load this, remember stress, strain, there's all this closure, and then we get this region of linear, and then we get this region of crack initiation, and you start hearing all these cracks, and they're going like this. But notice, when I push it this way, you get a crack, but that crack is not getting stretched as much. It's getting stretched a little. When I push it, it generates tension, but then the crack forms and the tension goes away. That means now the load goes to that, and now this guy cracks and the tension goes away, and then this guy, and they go all over the place, and they're stable. But if I took that same rock and I did a tension test, we typically get like one crack, and now it's like a fracture mechanics thing. Oh my God, now it's going to just boom, boom, boom. It's going to rip itself apart. So actually, fracture mechanics is contributing to a tensile test failure as well. Okay. Enough said. That was something else. Okay. So it's 9:30. Let's see, what's the next step here? I think I'm going to go back. Yeah, okay. I think I've said what I want to say about actual properties of rock that we're going to try to match. So now I'm going to go back and stop sharing. I'm going to try to stop sharing. How do I do that? Just a minute, that's not it. That's not, this is it. Come on. Stop presenting. Okay, tell me if we're back. Are you back to my screen? No.
Not yet.
Okay.
No.
Yeah.
You have stopped screen sharing. Okay. Now, are you back to my screen? Ah, now I have to share the screen on this side. Second, my PowerPoint is doing weird things. Just a second. There. Back. On. Come on. There we go. Now, I think we're back in business.
Yep, we can see it now.
We're back in business. Okay, hang on. For some reason, when I'm doing the display mode in PowerPoint, when I hit escape, it's not kicking out of the display mode. So I had to shut everything down. Okay, it's 9:30. Let's go a little farther here. So, what are the properties? Well, we've talked about that. What are the lab tests? Direct tension, UCS, triaxial. Yeah, let's do this instead of just jumping in here. Okay. What we're going to do now is we're going to go back to that odometer test that we had created. And remember, that was a granular material. We had the linear contact model, so it could only sustain compression. And let's simply go and put the simplest possible bonding idea, which are contact bonds, and then let's see what effect it has, okay? So we're going to go through this in a kind of ad hoc way, just like when we built that odometer test, we just like kind of hacked it together. We're going to do this in this ad hoc way, talk about a little bit about it, and then we're going to talk about the material modeling support package that's going to let us build and test these things very, very easily. Okay. So, just a minute here. All right, let's go. So I'm going to go back to the lectures and tutorials. We had this thing called odometer test. And what I did is just before, that's the original one that we had. So I copied it. In fact, let's get rid of this. Okay, that was the original one. So now I'm going to copy it. I'm going to start modifying it. So I'm just going to rename this directory. I'll call it odometer test bond me. Now let's go in here. So this is what I always do. I don't remember what we did, but remember we set these things up in such a way that we had a do all at the beginning. Here it is. It's going to do a gravity pack and it's going to run the odometer test. So let's look at the gravity pack and let's just run this thing to see if we can remember what we did here. We took a cloud of particles, we generated them, and we have gravity on, and now we're just letting them settle. And we're doing the solve ratio average till we get to 1e to the minus 5, which should be static equilibrium. And then we're done, and we made a save file, gravity pack, right? And then we run this odometer test case, and let's just stop part way. What we did is we restored the gravity pack, and then we created a wall at the top. Let's just do that. And we screwed around. We positioned the wall just above the topmost particle. So boom, we made that. And we did that because we wrote this function, get top y coordinate. We looped over all the balls to determine that, and we use that to create the wall. And that's going to be the platen, remember? So here's the platen, it's a global variable. And then we go and we define functions to compute axial stress and compute axial strain by looking at the wall forces and the wall displacement. Remember, we wrote this cool thing, get the coordination number, average number of contacts per grain. We set up histories, Platen force, Platen displacement, sigma y, epsilon y, stress strain, coordination number. So those are going to get monitored. We're going to sample them every single step. And now we're just going to load this thing. And let's do this one. We're going to load it. We're going to unload it. So we're going to make the velocity close for 7,500 steps. We're going to make the velocity open for 7,500 steps. And we were monitoring axial stress, y-axis, versus axial strain. We're just getting that force pushing, right? Everybody with me? Remember this?
Yep, remember this.
Yes.
Okay. So this is an odometer test. It's a granular material. And you can see how it starts stiffening originally. And that's because you get new contacts forming. And now it's pretty much not doing much of anything except squeezing the springs. And now we're pulling the platen back. And we're tracing the unloading curve. And if you recall, the area under the unloading curve is going to be less than the area under the loading curve, which means what?
Means
that
there are
telling me?
some energy goes other way.
Exactly. And where's that energy go? In this system.
Maybe
How
heat.
does it? What?
Heat? Is that the word?
Heat? Heat because of what? What's happening?
Well, because of the fraction.
Because of what?
Is that called
Friction.
Oh yeah,
Correct.
friction.
Because there's frictional sliding. Once it slides, you lose that energy. So there's a bunch of sliding going on. So this is what we got. And now it's unloaded. It's not touching. Force, axial stress, force is 0. Here's the curve sitting down here, right? And we also were monitoring during this test. This is the force on the platen, right? And we made compression positive. So you can see it loaded up, it got stiffer and stiffer. Now the force is going up, and then we move with the other way, force goes down. And we also looked at coordination number. So if we plot that on the same axis, looks like this. And this seems to make sense, right? As the force gets bigger, the average number of contacts get bigger. And then as we reduce the force, so this is that coordination number. Does this make sense? Remember this stuff?
Yep.
Yes.
Okay. So let's go back here and let's make a quick snapshot of this in our PowerPoint world, and let's measure the modulus. So this is how I always do it. I'm going to turn off the balls and the walls and turn off the force chains. I'm just going to look at this. I'm going to go up here and say bitmap. Let's just call it F1. It's going to go in the default directory where it was being run. I'm going to go in that directory. There's my F1. I drop it in. There's my stress strain curve. Axial stress, axial strain. And based on what we were saying, this slope is what we're going to call what? What's the slope of the stress strain curve?
Constraint modulus.
Ha! Nice job. It's the constrained modulus. It's not the Young's modulus. This does not have the boundary conditions of a Young's modulus test, of a UCS test. Let's take a quick peek at what I mean by that. This is actually pretty cool. I didn't know any of this stuff when I started doing this work. I'm going to pull out in this material modeling support package. There is this material modeling support memo. And in there, we talk about all kinds of things. Pretty much everything that I know about bonded particle modeling is in this 90-page memo. And you guys have it. Measuring elastic constants. It's in an appendix because it's a kind of detailed thing. Let's just do a quick look. I'm not going to work out the details, but let's take a quick look. This is very important, actually, that you understand this, and you guys can work it through. I'm going to go kind of fast. This, if we want to get E and nu, we have to have a linear elastic isotropic material. So theoretically, the stresses are related to the strains for a linear elastic isotropic material, and this is what they are. There's the strains, epsilon and these gammas. These are the shear strains, the engineering shear strains. These are the direct strains. And these are the stresses, sigma x, sigma y, sigma xy. This is the shear stresses, tau xy, etc. There's 6 stresses and 6 strains, and those tensors are symmetric. And so we talk about E and nu. Here they are, E and nu. So this is the relationship between stress and strain for the whole entire system. And theory of elasticity is a 3D material, is a real 3D thing. So you always have to start with the 3D relationship. And so the question is, can we apply initial conditions to a system to do a test so we can back out the value of E and nu? And we can if we take this system, cylinder, squeeze it with sigma z, or if we don't really apply sigma z, we apply delta z, we measure sigma z, and then for the general case, we have confinement that's constant, PC. So you see the idea, right? This is what we talked about. This is a triaxial test. For those boundary conditions, what are those boundary initial conditions? All the direct stresses are equal to the confinement. Think about it. If I'm squeezing it with that thing, if I'm squeezing it here with hydraulic fluid, I also, to be in equilibrium, what I also do is I take the platen and I push it down so that everybody is the same. PC is the same everywhere. So those are the initial conditions. And then I'm going to start pushing this down and I'm going to keep that constant, the PC. So what are the initial? Those are the initial conditions. During the test, sigma x and y are constant, but sigma z varies. That's the axial direction, okay? And so the other thing is right here, equation 28. This test has been set up intentionally to produce the simplest possible stress state, which is called uniaxial compression. The only thing that's going on, the only stress component out of all 6 that's not 0 is the axial stress, okay? And so we just can go back now to these expressions and simplify them by putting in zeros for everybody except for sigma z. Are you with me?
Yep.
Okay, super cool. So for these conditions, we can end up rearranging things so that we can just isolate the Young's modulus, and it's going to be the change in axial stress over the change in axial strain. So if we plot axial stress and strain, that's the slope. And the Poisson ratio, by doing simple manipulations, is going to be the change in the the change in the radial strain over the change in the axial strain. And there we go. That's what we do. So this is the real proper, this is a triaxial test. Nothing to do with a computer model. This is how we do and interpret a test, okay? Like this. And so even if, so it doesn't matter what PC is. Even if PC is 0, these same relations hold. This also tells you that during a triaxial test, you can still keep getting E by taking and nu by doing these things, even if you have as long as PC is constant. And think about the odometer. The confinement is not constant. The more you press on the top, the more the pressure on the sides gets bigger. And so this would be a good one, Ayad. If you had more time, I'm not going to make you do it, but I could say, figure this out. This is, now you know what to do. You would start with these equations and you would apply the conditions of an odometer test here. And then you would go back and remove terms and everything, and you would come up with something. And what you're going to find is that this ratio is not E. It's going to be something else. And that's what they call constrained modulus. Okay? You with me, AI?
Yes. Yes.
Okay? Okay. Now, this is crazy big deal important. There's so many people in literature who don't understand this. Now, let's talk about a biaxial test. Okay? Well, first of all, what the heck is a biaxial test? A biaxial test is a different test. It would not be a cylinder. It would be a block of material See if I have a picture here. It would be, you could think of this as a thin plate of material, okay? Same thing, linear elastic isotropic material, but it's a thin plate. And so a biaxial test would be performed by applying confinement on the sides and pushing it from above and below. And if you think about this, that's not enough to define the problem, because this is a linear elastic material with a certain thickness. It's like a big hunk of your countertop. Well, what's happening on the free surfaces here? There's one in the front and one in the back. And so depending on what we do with those free surfaces, it's going to behave differently. And so what people typically do is they solve for two conditions, which are extreme conditions. They say, let's assume that the free surfaces are completely free and nothing is pushing against them. And what that means is that they call that plane stress. And what that means, think about this, you squeeze this, it's going to bulge out. Those free surfaces are going to bulge out, right? Because of the Poisson effect. Are you with me? If you took this and made it a plate,
Yep.
you squeeze it, it bulges out. Okay, that's plane stress. But you could also put this, you could put two plexiglass plates here that are infinitely stiff and that are lubricated. And now when you squeeze it, it's not going to bulge out. It's going to have zero strain in the out of plane direction. They call that plane strain. And a plane strain boundary condition is going to be stiffer overall because now it's confined. It's going to be stiffer. And so if you do a two-dimensional problem in theory of elasticity, you have to specify what's going on in the third dimension. Okay? And so any computational scheme in a continuum mechanics world, as soon as you run a 2D code, you always have to check a box. I'm running a 2D problem under plane strain or under plane stress. And of course, you could have other weird variants, but in almost all cases, you only consider plane strain and plane stress. So that's proper theory of elasticity. Then the question arises, if you model this as a whole bunch of balls, and which are like disc, unit thickness discs, and you squeeze that, what the hell is that? Is that plane strain? Is that plane stress? So think about it. You got these discs, they're like pencils. Well, you could do this in a physical laboratory, right? You could take cylinders, like acrylic cylinders, that are a unit thickness in depth, and you could stack them together to fill up a rectangle. It'll look just like a PFC model, PFC2D model. And those cylinders, you could just have them sitting there, and you have nothing in the front and the back, and you could load those cylinders, and you would get some force displacement response. But you could also now put some rigid walls in front and the back, and you could load those cylinders, and it would be stiffer. You would get a different force displacement response. And so the question then arises, is a PFC 2D model, any 2D DEM model, is it plane stress or is it plane strain? And there is no good, fully proper answer to that, basically. You could say it's plane stress because there's no stress touching the ends of those cylinders, but you could say it's plane strain because it's not straining either, because the cylinders are rigid. They don't bulge out. And so it's the fact that they bulge out that makes plane strain affect things. And so it's not a 3D continuum. It's a bunch of cylinders. A bunch of cylinders are not a 3D continuum. So it's this weird interpretation problem. So what people do is this would be, I talk about it here. If you make certain assumptions about what's happening, you can remove some of you start with the 3D relation and it turns into this. Because the only thing going on in the PFC 2D world is strain in the X, strain in the Y, and there might be some shear in the XY. There's nothing else in that world. We never compute anything else except the X and the Y stuff. And so you could basically then go through the same analysis we did before, and you could come up with, notice this thing, I'm calling it E prime and nu prime. I'm going to call this the effective Young's modulus and the effective Poisson ratio, because it's not exactly the true one. It's the thing you get from a 2D discrete element model. End of story. And so you end up getting the same relationships. There you go. E prime It's the slope of a biaxial test with no confinement, stress over strain. And the Poisson ratio is, again, the bulging out over the squeezing down. And so we do the same things. We measure the same things, but what we're really computing is we're not really computing E and nu. I'm going to call these effective E and nu. I could show you like hundreds of published journal papers where people have never thought about this. And they just immediately use these expressions and they say, oh yeah, that's E and that's nu. And then they just kind of say, oh, it's plain stress. But it's not necessarily, you can't necessarily say that. So nonetheless, if you do this and you define E prime and nu prime this way, and you build bonded particle models this way, it all makes sense and behaves pretty much like a real triaxial test with PFC3D. PFC3D does not require this weird E prime and nu prime because PFC3D is a 3D thing of grains, and there's no weird cylinder business going on here. So the PFC3D satisfies all the conditions of a true triaxial test. Thus, you can compute the real E and nu by these relationships. Okay? Does that make sense?
Yes.
Sort of? Questions? Okay. So this thing, this slope, oh yeah, this is the constrained modulus. So we're not even going to go any farther here. In fact, this is good, Ayat, that you remembered that, because what I was thinking when I set up the lecture, I was saying, oh, this is E prime from the odometer test, but it's not even E prime. It's some other thing. It's basically just the stiffness during an odometer test. Because what I want to do now is I want to bond this together, and I want to measure the E prime. Okay, so let's just leave this here. So we're going to go back to this. So here's our system. What do we have to do to make it, to bond it? So we have to, what we're going to do is we're going to go after the gravity pack. That's the save file. Now they're just sitting there. They're granular. And we're going to take this thing and we're going to go to every single contact and we're going to say, I want to make this a contact bond and I want to give it some strength. Okay. And if I do that, now it has strength. And so now I could remove the sidewalls and it's going to sit there, right? If I remove the sidewalls now, it's going to just fall apart. Okay. So is everybody with me? We're going to add bonds.
Yep.
Okay. And let's take a quick refresher of what we mean by a contact bond. Simplest possible idea. Start with the linear model, normal stiffness, shear stiffness, friction. Think of a piece of cement that's infinitely small piece, no radius, just a tiny, tiny thing. And so then what's that going to do? When you pull it in tension, there's not going to be a gap. There's going to be a fuse. It's going to resist tension until it breaks. And same way, there's no friction idea anymore. It's a fuse. It's glued. So it's going to reach a certain critical value of shear force at which it'll break. So these I'm going to call strengths. And I've argued that there has to really be two fundamental strengths, just like there's two fundamental stiffness. Normal and shear, there's going to be, I'll call it a tensile strength and a shear strength. Okay. And so that way then, remember this is the linear model in tension in the normal direction, right? If you pull it apart, it sustains no tension. If you push it together, it goes up forever with the normal stiffness. If we put in a bond, now it's able to pick up tension until it reaches the tensile strength, at which point, boom, goes to can't carry load. And then same thing here. This is frictional sliding in the shear direction. There's the friction coefficient that limits it. But if we glue it, this is just going to keep going. Now it's going to go up until it reaches the strength. Boom, it's going to break. Okay, with me?
Yep.
Okay, so the only difference is that now there's two additional parameters right there, TF and SF. Okay. And what we want to do, think about this. This is an interesting point. If you're going to make a bonded material, if you're going to make a rock, think about a rock. You have to get those grains and you have to somehow pack them together to begin with, like a sandstone. The grains get packed together first. They're a granular material first. They get packed under some pressure and then they get cemented. If you made a cloud of grains and you just cemented the ones that were touching, you'd have some weird thing. You have to first pack them and they have to behave as a granular material first. Okay, then we're going to put in bonds. Okay, and this is what we always do, well, almost always, when we build bonded systems. Okay, so that means I'm going to run it through the packing process and I'm going to make it behave like a linear material, which means it's going to be not bonded. Well, to do this, after I'm done, I want to turn it into a contact bonded material. So this model is actually called the linear contact bond model, because the model, when it's in an unbonded state, is actually the linear model. But when you say bond it, you're going to give a command, bond me. And when you bond me, suddenly it behaves like a bonded system. So are you with me? So we're going to have to, during the gravity pack, right here, this is our famous CMAT. What we used to do is this, model linear, property, KN, KS, and fric. But if we did that, it's not a contact bonded thing. We can't bond it. So what we're going to do is we're going to run it like this. The linear C bond model. We're going to give the same KN, KS, and fric. And then now there's these two additional parameters. And for now, we'll just set them to 0. They're not going to be used until we bond it. Okay. So we'll run this and we'll watch this thing. So this should be giving us exactly the same answer as before, because if it's unbonded, and by default, it's always unbonded. It doesn't get bonded unless you give a command to make it bonded. Okay. So there we go. And let's just see if we got what we think. Let's go to the ball plot item and let's say color by, what are we going to do? No, we got to go to the contact. We got to make a contact plot item. And we got to say models. No, we got to say types. No, we got to say numeric text value. Contact model name. Contact model name, red line, linear C bond. Those are the linear. So now that's what we have at all these things. And it has a state now. You have to be able to say, are you bonded or are you unbonded? And so there's a concept of a state. The model is in a certain state. And so let's look what that is. Contact models, built in, linear contact bond, properties. And right here, CB state. There's only 4 possibilities. You're either unbonded, or you're bonded, or you're unbonded now because you've broken tension, or because you've broken shear. Okay? So this state variable is going to always be one of these numbers. So what should it be right now? What should it be equal to right now?
0.
0. So let's see.
Oh, yes, 0.
0. So it's going to be CB state. We got to make it. Oh, there it is. CB state named 0. So this is telling me there's a contact bond. Linear contact bond is the contact model. It's not Hertz. It's not linear. It's linear contact bond. And it's currently, all of these contacts are unbonded. Cool. That's what we want. Now we want to bond them. So let's go into the odometer test. And at the very beginning, got to make them bonded. So again, let's run it, restore, just make sure this is working. Boom. There they are, not bonded. Now, we have a thing to bond it. We actually have a thing called a method. A method is a computer science term. It's like do something to something, and there's a way to do it. There's a method to do it, okay? So we have a method that's going to be called bond. And let's see if I can remember the syntax. Every single contact model has a thing called methods. And here it is. Bond. There's also an unbond. So if I go here, bond, create a contact bond by bonding the interface. If the contact gap is within a certain interval. If no gap is specified, then the interface is bonded if there's overlap. Okay. So let's try to call this method. The command should be method unbond, and then there's a gap parameter. So let's see. Method unbond, no, sorry, method bond. I want to call this on all contacts. Method bond, and I got this stupid gap. Let's just try this. This is not going to work. It's going to tell me bad conversion of method. Oh, and the command is actually, it's a contact command, contact method bond. Boom. Oh, look at that. So there's a method called bond, and it got applied to 336 contacts. Okay. And I could have given a range here. I could have said only apply this, da, 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 da. So let's look at what it did. Contact, CB state, oh, boom, 3. Okay. But let's look at this carefully. What did it actually do? What did it actually do? There they are, little red guys. Make them a little bigger. What did it bond? It bonded the particle-particle contacts, but look at this. It also bonded the frickin' contacts to the wall because I didn't give it a range. I just told it every single contact. And as you remember, some contacts are ball-ball and some contacts, contact type. Ball-ball, the blue ones, ball facet, those. And maybe we want to do this, but we don't. In this case, I only want to bond the material inside. Are you with me? Are you with me?
Yep.
Okay. No, my God, how do I do this? Range. Oh, my God. Contact. Let's see if I got this right. Contact type. Let's try this. Come on. Bloody hell. Contact. Oh, maybe it's just type. Come on, work. Type. It doesn't want this. Range. There's a stupid range command that makes it apply. Type. You can see what I'm trying to do, right? I only want to bond the guys who are ball contacts.
Is it range set as we did with the wall?
That's a good idea, but that's not right. That's a super good idea. I hate PFC because when they rewrote it, they made it so freaking complicated. But it's hard. You don't know how to make it any less complicated because it's doing so many things. It's so general purpose. Just a second. There's a range command. Let's duplicate this. Range set type, range group. Wait, I'm going to look at one of those earlier tutorials, the really easy one, because I think we screwed around with this because we were doing different, like make layers.
That's what I usually do.
Okay, but this is a group thing. We're not talking about group. It's not a group thing. It's no, I don't do this here. Tag type. Okay, see, I'm you now. I'm trying to freaking figure out what to do here. I'm gonna search for range. Look at a command, model summary, command. Where's commands? Linear contact model. I got to go to contact, and let's try to search for range. Range element. That's not very helpful. Range, I'm going to get like 7 million hits. Range. This is the idea of a range. That's not helpful. I want the range phrase. Model range. That's a range. Here we go. Range phrase. Range something. Okay. Where one of these things must say contact type or something like that. Help me if you see it. If you see this. Contact range contact type. Okay, so I got to say range space contact space type, because it says based on type, and these are the types: ball, 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 pebble. Okay, sweet. Let's see. Range contact type ball, ball. Boom. Ooh. It only got applied to 310. Last time it was 367. We might have done it. So those are the contact type. We want to say state. Numeric value, CB state. Come on. Oh, I think we got it. 0. That means unbonded. Those are ones with walls, but 3, bonded. Okay, we got it. Agree?
Yep.
Okay, excellent. So this is add contact bonds, or not add, they're already contact, bond the ball contacts, not ball wall, not ball facet. Okay, so now we got something bonded. So let's just see if we get up to here. Great, turn that off. There we go. We didn't affect anything. We just suddenly changed the state, so now it's bonded, okay? Now we could actually squeeze it. Nothing, it should just behave differently, right? Let's just run the same thing. Never done this before. And let's look at the history. It's going up. And now there's no frictional sliding going on here. Oh, except, wait, I didn't give it any strength. I think they're all going to have probably broken. State was, a whole bunch of them are now in state. Let's see if we can understand this. This is important. It's interesting. So state 0. That means they're unbonded. And state 2 means that they broke in shear. Sorry, they broke in state 2. Unbonded and broke in shear. So there's a bunch of them that broke in shear, and there's a bunch of them that are simply still unbonded. Okay. Why are they unbonded? Trying to remember. Let's not worry about it here. Okay. Because those are new guys. That's right. As we start squeezing this, okay, look at this. Look at this. It's so subtle because the microstructure is so subtle. Check this out. Watch this. We're bonding them. Whoops. What are we doing here? Run this. Bonding them. Boom. Bonding them. Look at the view. Okay. Those guys are unbonded. Those are bonded. Now, look at this. Like, let's look at this guy here. So let's not look at the state. Let's look at linear C-bond active. They're active if they're overlapping. What if we show all? Oh, this is linear C-bond inactive. Remember this? There can still be contact bonds, but they're not touching yet. Okay? So that means this guy is sitting there and there's not a gap. But the bond method only bonds them by default. Create a bond by binding the interface if the gap is within a certain interval. If no gap is specified, then the interface is bonded only if the pieces overlap. Okay? So that means these guys are not bonded, but they're still ready to go. So when I push this thing, these guys come into contact, and that's why they're unbonded. Are you with me?
Yep.
Okay, so CB
It is a
state.
bit confusing.
Okay, so go back to this again. Just a minute. Yeah. Good that you're asking this. Okay, contact. Wait, what am I trying to do? Hang on. It is confusing. Here we go. Here's my microstructure. This is all of these guys have the linear C-bond model. With me? All of them do. And some of them are active and some of them are inactive. You with me?
Yes.
Okay. And the definition of active here means that they're overlapping. Okay. And so this is what I see. This guy, let's turn that off for a minute. These guys are actually overlapping. So they are active. These guys are going to be inactive. Let's turn them on again. There, this guy's inactive, and this guy's active. Okay. Now, when I give the bond command with no parameters, it's only going to bond the ones that are overlapping. So it's only going to bond the ones that are currently active in this picture.
Okay.
Look at the gap. The gap, if it's negative, means it's overlapping. So it's only the blue guys that are going to get bonded. This green guy has a positive gap. This is a better way to think of it. It's only the blue guys that are overlapping. When I give that bond command, by default, it's only going to bond those guys. Are you with me?
Yeah, makes sense.
Okay. And so that means if I start pushing this, these guys are eventually going to come into contact. So just a second. So we should be able to see this. Let's just watch this guy. Let's see if he comes into contact. He's not in contact now. He's unbonded. 0, unbonded. Let's put him in the center. Let's turn this sucker off. Let's just run this now and start squeezing it. Whoops. I must have a return in here. There we go. Start squeezing it. Yeah, this guy. Watch this. Come on. Go into contact. Boom. Went into contact. Stop the run. Now let's look at that guy. Let's look at the state. State. Now, this guy's 0, unbonded. But now he's there because he's active because they went into contact. Okay. Guys with me?
Okay, yes.
Okay. You're starting to see this microstructure is very sophisticated, and this is the simplest possible model. You have a system that's packed, but you have a lot of guys that are close to each other. And now you're going to put in cement, which I'm going to say bond. And the question is, does the bonding fill the gaps or not? So by default, it doesn't fill the gaps. It just gets put where they're touching. But now you've got this system with these small gaps. So when you start compressing it, it's going to start getting stiffer because it's going to make these new things. So effectively, this initial system that we created had a whole bunch of gaps in it. And those gaps are beginning to close. And there's no breakage or anything. Well, there's breakage here too. We're going to get rid of that in a minute. We're going to give some infinite strength. But do you see what's going on here? Okay. And when we make the bonds, we can do more than this. It's default. We could go and tell it, I want you to bond everybody that is closer than a certain distance apart. So I want you to fill a certain size gap with cement. Okay, so we could have given a command in such a way to do that. And if we did that, we'd have more cement in here and less gaps. And so we would be stiffer and we would have greater strength. Okay, you with me? You with me?
Yep.
Yes, someone.
Mm-hmm.
Now, Also, this initial state, the amount of gaps that are closed is going to be related to the coordination number, which is going to be related to the pressure that I'm squeezing it with. Okay? The more I squeeze it, the more I close those gaps and the more contacts I have until I reach some point where I've like squeezed it so much that it's not changing anymore, right? Because we saw that for the granular case. That's why the coordination number keeps getting higher and higher for a while. So if I take the initial state and bond it, I get a certain amount of guys that are touching that I bond, 310, whatever. If I though squeeze it for a while and then bond it, I get more cement, I get more bonds. Okay. So it would be like, sandstone. You just deposit. Well, it's exactly like that. You could see how this would happen. Imagine you do a test. You put dry sand in. You just fill it, let it sit there, put in bonds where it's touching. Maybe you could heat the thing and they would weld together. And it would only be the guys who were touching that would weld together. But then go and run your odometer test for a while. Now you have a lot more packed system. You have a lot more contacts. Now heat it. Now you're going to get a much denser amount of bonds. And that's going to be stiffer and that's going to be stronger. Okay? So the bonded system you build is sensitive to the initial conditions of the packing at the time you bond it. And there's no way to get around this. You really do have to pack this stuff and then you have to bond it. Are you with me? Is it making sense?
Yeah, it makes sense.
Okay. And so what we're going to find is with this material modeling support package, that's going to be a key parameter. It's going to implement a packing procedure that's going to isotropically compact the system until it reaches what you tell it to in terms of pressure. So if you make the pressure small, it'll pack it to a small pressure and then it'll put in bonds. Or you can pack it to a higher pressure and put in bonds. And in addition, there's going to be a parameter which is what I call installation gap. So you can say, you're going to say, put it to a certain pressure and then put bonds everywhere where the gap is within a certain distance. And then that's going to put in bonds there. This way, you have a controlled way of building a material that's well characterized. If you were to just let them rein in under gravity, you have a very loose microstructure. But now, and also when we do the construction process, we're going to have no gravity. So we're going to squeeze it uniformly from all sides so it's isotropically compacted, meaning that its properties are the same in all directions. And we're going to press it till it reaches a pressure we want. And typically we make that pressure low so there's not big overlaps. And then we're also going to tell it, I want to bond everything that's within a certain distance. And it's going to fill the gaps. Okay. So we have a controlled way of building a microstructure. And so that initial pressure and that installation gap, I call it, are fundamentally parameters that are affecting the overall final material properties of the bonded system. Okay. And this is exactly what would happen in a sandstone. The sand gets compacted over many years. It's at a certain pressure because of the depth. It's got a certain amount of packing pressure, and then it gets cementation process. But then you might have other sandstone that's deeper down. So it's even at higher pressure, and then it gets cemented. The one deeper down, if the cementation process was the same, the one deeper down is going to be more well connected. It's going to have more cement. It's going to be stiffer. It's going to be stronger. Okay. Because we're actually diagenetically constructing the rock. And the other thing is the packing that we get is totally controlled by the force chain distribution. And so if we change the size distribution of the material, we're going to get a different overall force chain network. And if we change the shapes, we're going to get a different force chain network, which means we're going to get a different fabric, we call it. A fabric is a way of trying to quantify the connectivity properties of a packing of material. And in fact, I just sent AI some stuff about mathematical ways of quantifying fabric. And so the initial fabric at the time of bonding is going to be critically important to the behavior. Okay? Like if you squeezed it and you had very little confinement, most of the forces are going to be lined up and down, and you're going to have more contacts oriented up and down and less contacts oriented this way. And so then if you put in cement, you're going to have less contacts this way, which means if you measure the stiffness this way, it'll be smaller than if you measure the stiffness this way. Okay? That's why the material modeling support package, in order to create like the simplest possible uniform system, is isotropically compressing it to start off with. Okay? And so I think you're starting to get the idea of the richness of the microstructures that can be created with this. This is much more sophisticated than you would have thought. It's certainly much more sophisticated than I would have thought when I started doing this work. It was like, oh, it's pretty damn simple. You just throw these in a box and you glue them. And it's like, well, wait a minute. The state at which you glue them is important, and that's connected to all sorts of things about the behavior of the granular system. Okay? And most of the things that affect it have never been really systematically tested. In almost all cases, the people who've done research and use these types of models, they typically just use the simple case of the initial well-connected system with the material modeling support, and then they look at stuff. They try to calibrate, and they look at different problems, right? But if you change those initial packing things, you will change fundamentally the character of the system. And so that's why I sometimes talk about there's a microstructural space that these kind of models possess, and that microstructural space is vast. Just changing the size distribution will fundamentally change the behavior of that bonded material. And so that's why this is cool from the perspective of as a research tool, because it's really wide open. Like there is study that could be done to gain better insight into how these things should be constructed, and to how you could construct them in a way to try and replicate specific microstructures of real rocks, right? You could construct this the way sandstone is constructed, and that's kind of what we're doing here. We're letting it rain in under gravity. Then we could be applying overburden loads, and then we could be putting in cement, right? And then we could be unloading it just like you're taking out a core. Or you could say, oh no, this is like a granite. We're going to put a bunch of particles so they're not touching, and then we're going to slowly expand the particles, which is similar to a crystal forming and growing outward. And then you get a completely different packing. And you could say that would be an initial microstructure for granite, which would be different than letting it fall under gravity and compressing it. So that's what I want to say here. And we're going to go back and we're going to now run this thing. But I think what we should do is first take a break. We've already gone for a really long time. Let's take a break on it. So what are we going to do? We're not going to screw around. We're just going to bond in this crude way, the guys that are touching. And first we'll just run it just like this. So we're still doing an odometer test, but we've actually glued the thing together. We've glued it together. And here we're going to get crazy stuff here. This is the force displacement, right? Let's just do a quick thing and plot this force displacement next to the other one. I'm just curious. It definitely should be different, but the question is how much different. Here's the other one right there, stress versus strain, but with no bonds. It's just frictional, but now we got bonds. Oh, hold on. This is useless. The bonds have zero strength, so they all broke. Let's go back here. Because when we first created it, we put a CMAT and we said strength right here, 0. So we don't want 0. So now we want to bond things and we want to set the strength. So we have to say contact property. And the property is the name of that thing, which is TFSF, tensile strength, shear strength. These are force units. CB10F, CB10F, and let's make it infinite, 1E20. And CB shear strength, shear F for shear force units, 1E20. Just see if that worked. Boom. Try again. Boom. Properties set in 336 contacts. That means we're probably okay. Let's look at the contacts in there, and let's look at the value of tensile CB10F, 1E20. So I think we did it. And we also set the strength here for these unbonded ones, but we don't care because they're unbonded. So it doesn't matter what the strength is because it's not going to use it. Okay? Okay? Okay?
Okay.
Okay, excellent. Now let's run that crazy test here. Oh, wow, it's different already. It doesn't look like it's increasing as much. Well, maybe it is. Let's just see. So we're loading this for a certain number of time steps, which corresponds, we're not controlling the strain. We're just doing time steps. And the time step might be different here, so we might not get the same amount of strain. So this might actually go too much. Let's see, because if they start overlapping too much, it's going to be crazy. And oh, there we go. Now it's unloading. I just want to do a quick, let's just plot this thing. So the total maximum axial strain was like 1.6 e to the negative 1. This was like 1.6 e to the negative 1. So the time step didn't change because we're doing the same number of cycles. And this thing reached 5E4 in stress units. Ooh, and this one's different. Let's look at the other plot. That's force. I don't want force. No, and that's now let's look at this plot. Here, let's turn off all this extra junk here. There. Stress versus strain. We unloaded it the same amount. It's still carrying a little load, but let's make a plot of this. Call that one F2. New slide blank. Suck in F2. Wow, what's going to happen? Let's see. Odometer test behind me. Boom. So this one got up to 7. That was bonded by the time I applied that much strain, and this one only got up to 5. Let's just do a quick thing. Let's go and make the same axes on these things. So this one, let's just change the axes here. Let's put the Y max. How do I do that? Go to the history plot item, axis 2, which is Y. Make the minimum be 0 and make the maximum be, let's do 8 e to the 4. 8 e to the 4. Okay, that's what we're going to do. Let's make that plot when it's bonded. Bitmap. F3. Suck this one in. What are you expecting in terms of stiffness and strength? What are you expecting? How will the stiffness and strength differ? And will they differ? What do you think?
Supposed to be more stiffer or like more strong? Have a
I
higher
would think it
strength?
would, yes, I think it'd be both. So what are we doing here? This time we're gonna, okay, so this time, how could we do this? We're just not gonna bond it. Boom. It's the linear C-bond model again, that's fine. But if we don't make it bonded, it's just gonna be granular. So now let's run this. And now we got this y-axis fixed. So now we're watching this thing. It seems to be a hell of a lot less stiff. We'll make these plots together, right? This is like cemented sand. I don't know if you remember, Marley Reed is the person who did that work for biocemented sand, and she actually did this. She put sand in a cylinder, and then she put a bioagent that cemented it. And she was looking at how it was going to behave. This is exactly what she did.
Yes, I remember.
Wow. Ayad, I think you nailed this here. I think you're right. Let's see. Now let's just make, yeah, so now if we make this plot, we can just compare those two images. I'm going to assume the x-axis will be the same. It looks like it's going to be the same. Let's do bitmap, G1. Here's the unbonded case. Okay, so unbonded, bonded. Oh my God, look at the difference. So unbonded, it's very, very unstiff because it's just moving itself around. It's not until it gets kind of in a packed state that it starts being stiffer. Whereas the other one, it's very stiff to begin with. Comparable, right? See, look at this. The stiffness is almost zero. The stiffness is definitely not zero. And then it much more quickly kind of gets to be the same. This is because those initial gaps, we didn't put cement in those gaps. So they're closing up. And now pretty much it's the same. Nothing is really changing. That's why it's pretty much linear. And now we're unloading it. What's the other thing about energy between these two systems?
Less
Look at this one.
energy. Less
Yeah,
energy loss.
I would agree. I mean, we'd have to quantify it, but I think that's the case. This is a bigger hysteresis loop. This is a bigger difference when it's unloaded. There's a lot of energy loss in the sliding. There's no sliding. Well, now let's try to unpack this. This is very complicated. This thing started breaking, and as soon as a contact breaks, it is now, sorry, it's not breaking. It's not breaking. We made infinite strength. And so it's still an elastic system, but the nonlinearity here is because those new springs formed. Okay. Those gaps closed. I'm not sure why it's not exactly the same then. And I don't want to think about it. Let's make sure that nothing broke. We didn't save it. Let's quickly run it again. We're going to run it out to here, and we're going to say model save, and I'll call it halfway. P2 save. Well, we don't even have to do that. Let's just look at the state, and let's make sure that nobody broke. So this is the end of the test. So the state, CB state. CB state is 0. Wait a minute, what's that? That means it's unbonded. Oh, wait, now I'm confused. Okay, this thing. Okay, help me guys. We got to unpack this. Oh, that's because this is the other test. This is the one we never bonded. Let's just make sure. Are you with me? You see what happened there?
Yeah,
Of course
it
they're
makes
unbonded.
sense now. Yeah.
Let's just make sure that this thing, nothing breaks. So let's look at CB state. 0 and 3. 0 is unbonded. Those are the guys who are the gaps are starting to close. And that's why they're unbonded and they're being shown because they're active. So if it breaks, it's going to be states 1 or 2. And it looks like not. So the nonlinearity is here, I think, because you're adding stiffness. You're adding springs and removing springs. Oh, and as soon as you add a spring, those two surfaces can have frictional sliding. It's the linear model. That's what's happening. There's still frictional sliding here, but there's a lot less of it. Does that make sense? AI?
Yeah, kind of.
Well, there's less
Yeah.
guys who are possible able to slide. Like the red guys, that's the backbone structure. That never changes. They can't
Mhm.
slide.
Okay.
So that's why we got this thing. This all makes sense. Good. Okay. Now we can actually do a UCS test. What do we have to do to turn this into a UCS test?
Remove the confinement on the y-axis.
Sorry?
Remove the vertical walls.
Absolutely. Let's do it. Now we got to be careful here. Let's see. Let's just go the platen wall. It's all going to get weird. No, it's not. Okay. We're only using the platen wall to compute the stress, and we're only using the platen wall to compute the strain. We're not using the side walls to do any computations. So that means we should be able to just delete them. So just before the test starts, delete the walls. Wall, delete. What are the names of those walls? Wall list. MV right and MV left. Wall, delete. This is the one AYAT remembered. MV right. And wall, delete, MV left. And then let's take a look at it. Just run this. It removed them. Let's see if it did. Boom. Now, this thing should hang together because it's bonded. So suddenly we've created a cemented material. So now let's see what it does. It's going to be super weak. Okay, let's just run it and let her rip here. Look at this weirdness here. Just go for a little while, then we'll stop. Stiffening. Let's look at it. Let's look at it. Let's look at the state. And I think we still have infinite strength. There's the state. Those are the black ones are the new ones. They're unbonded. There were the gaps that closed, and these are still bonded. So this is just basically the same thing because we haven't allowed it to break because we gave infinite strength. You with me? Yes? Yes? Makes
Yes.
sense? Okay. And I don't know what strength makes sense. Let's do this. No. Let's just do some super crude stuff here right now. Now we have two parameters, tensile strength and shear strength. Let's just go and keep the shear strength infinite and only let it fail in tension. And I have no idea what to put here. Oh, wait, let's see. No, I have no idea. Let's put 1e to the 5 and see what happens. I want to see if I get some breakage here. And there's no breakage. Remember, instead of 3, it's going to go to 1 and 2. So this is still too high to let it break. So we're just going to keep hacking it. Let's put it 10 times lower, 1e4. Come on. Look at this guy. Look at this guy, just hanging there, no force. Still no breakage though. Definitely changing a lot. Look at this microstructure. Still hanging together though. So you think of it as the backbone. Those red guys are the backbone.
It's really like fascinating.
It's just amazing. Look at this compression change. See that backbone?
Yeah.
It's going through reds. Here's it still going through here, but that's like compressed, so
Not
it's still carrying
connected.
that load, right? Most of the load is vertical, right? Like you could run your crazy AI, your stuff you haven't done yet, but the fabric thing. Okay, so it still hasn't broken. Now, see, if we were in the lab, it would have taken us a week to like do each of these tests. Now we're doing 10 times even less. Get rid of the force chains. Come on, you got to start breaking here. Ah, broke. One. Where did it break? Let's just look at the one. The guy with the one. Let's use the plotting. Oh, look at the stress strain curve. The force dropped because of that breakage. Oh my God. Okay. Let's see. Contact bond state 0, 1, and 3. Let's just look at turn off 0, turn off 3. Oh, right there. There's only one breakage so far.
There
And
was
just
I
go
saw
ahead.
like a few of them and then they kind of bonded again. Is this possible?
No, not unless we tell
Mm.
them to. That's not what's
Okay.
going to happen. Let's just keep running this a tiny bit. I'm just going to cycle more. The walls are still moving together. There's no load here. Here's another one. Here's another one. Here's another one. Let's stop it now. It's very weak stuff. Look, it's just like blowing out here. There's only load pretty much carried here. History. Look at that. Let's do a quick comparison. With this, we got to make the x-axis go to, I don't know, 1.6 e to the negative 1. Well, what the hell? Let's just do it. Let's just run it out to the same strain path. But it might have totally broken apart. I don't know. Let's see. Watch this force chain. When this thing breaks, this becomes very compliant and it's not carrying load anymore. I think it's this guy that's going to break. That's tension. Boom, it broke. Watch this force chain buckle. There, it buckled out. No more load. No more load on the outside. Still load. Black. Look at those micro tensions. Boom, that caused it to break. It's the micro tensions that are where it's breaking. As it breaks, the force that we measure has to drop. It's crazy. We've almost completely destroyed this system. It's still carrying load, but hardly any because the load is super low. But let's just go to that point, and then let's reverse now you're unloading it. Oh, it's already unloaded, right? See, it's not touching. So here we go. Wow, this is nuts. Just like crush that stuff, man. It just kind of like broke apart with hardly any strength. And you can see the curve. So that's plotted on the same axis. So let's do a quick plot of this. Let's just do one quick study because we're almost out of time. New slide, blank. What did we say? RRR, I think. So this was a case. We'll just do one more case. We said CB tensile force equals, I think it was 1 e to the 3. 1 e to the 3. And so this is in newtons because it's force units and we're using SI. Let's just run it. And we know that 1 e to the 4, it doesn't break at all. So what if we just make it, give me a number. What should I use? Bowen, what should I use?
Maybe 3.
Oh, got it. Good. 3 times stronger in microtension. And we're not allowing it to fire in shear. This may not be realistic, but we're not allowing it to fail in shear. So now, turn off the force chains. No breakages yet. No, I'm just not sure. Maybe there's no breakages yet. Now we already unloaded it. I think it didn't break. Yes. Oh, wait, state. Yeah. Showing everything, 0 and 3. Nobody broke. But it's a little bit of a different system. It was high. This is higher, remember? Let's plot this, and then let's take it again a little less. Okay. Duplicate. 3. What did I call this thing? Look at the comparison of the stress strain. 1e to the 3. Some guys broke. Nobody broke, but somehow it's, sorry. Nobody broke, but it's still stronger. The hell's going on? Oh, because this broke. It's weaker. Nobody broke there. So it's just going up. So let's do 2e to the 3. How does that sound? 1e to the 3 is super weak. Let's do 2e to the 3. We want to see some right here. We want to see some breaks. You know, we might not see very many because even with the weaker thing, there, somebody broke. Let's just look at the guys who broke. Bond State. Those guys broke. Changing all the force chains. Here's the history. There we go. Look at how crazy complicated it is. Somebody must have broke right here. Now it starts loading up again. Now somebody else broke so much that the entire system is in failure. Well, no, it's not in failure. It's just being unloaded, right? It loaded up. Somebody broke. It lost force, but now it's building up force again. Somebody broke here. Now it's building up force again. And now we unload it. So let's just take a quick plot. I feel like I'm playing a video game. H6. And what's our number? 2e to the 3. So that's 3e to the 3. Here's 2e to the 3. And what did I call this thing? H6. Okay, let's go. Just a second. There. Nobody broke. 3. Now let's look at the one where a few of them break. Look at how it's the curve. Look at how this first part of the curve is identical. See here? Goes up to here. Whoops, boom. It's identical because nothing broke. But now, in this case, nothing broke up to this point. So it kept going. But in the other case, something broke. Boom, she dropped down. And now it goes up. And if we make it even weaker, sorry, I'm sorry. These are out of order. Just a minute. And then we'll stop. 3, 2, 1. That's as strong. Now it's weaker. And now it's even weaker. Because now it failed way over here. Right? And as soon as it failed, everything changed and it got weaker. Okay? The initial stiffness is the same because it's not going to start changing stiffness really until these breakages occur. Okay? Any questions? We're going to wrap it up. Make sense? Any comments?
Yes, just I want to confirm something loudly.
Yep.
So for the bonds, we start with 0 and 3 basically, and then we should expect 1 and 2, right? In
Sorry.
any loading condition.
Sorry? What?
So my point is there is like the 1 and 2 conditions for the bonds states.
Oh,
There
yes.
is like it says unbond and broken in shear or in tension. So
Correct.
we should see the bond first before we see the 2 and 1 or 1 or both.
There would, oh, you mean, well, I'm only plotting right now the ones who broke in tension. I mean, here, I'm only showing, is that what you mean?
No, I mean in general.
Well, in this case, we gave infinite shear strength, so we're making it only fail. The only way it can fail is tension. So we
Yeah,
should never
okay.
get a state of 2,
Yes,
right?
okay.
And so what would need to be done here, this is, again, it's a vast microstructural space, right? You could then say, well, let's set tension and shear equal, and let's see what happens, right? Let's set tension infinite and just shear. And we can talk about that. If you set tension infinite and just shear, you're going to make it behave like a metal. It's not going to behave brittly like a rock like this. It's going to have plastic deformation. It's really crazy. So I love this example because it's like so simple, and it's illustrating all of the thus far, just the beginning of illustrating all these different rich things of how this system behaves.